So let's look at the mean, variance, and standard deviation for a continuous probability distribution. So when we have a PDF given to us from a random variable x and it's continuous, and we're asked to find the mean of the function. So we're looking at our mean is our Greek letter mu, kind of looks like a cursive U. And sometimes we'll actually list this as the expected value of x for shorthand, capital E with parentheses of x. And that is equal to the integral from negative infinity to positive infinity of x times your probability density function, PDF, f of x. Yeah. So that expectation or expected value or average is found using the integral. So that's your mean. The variance, so sigma squared is a lowercase Greek letter s, sigma. Kind of looks like a circle with the tail off the top. Actually, that's not very good. Almost looks like a delta that I drew. So I don't know if that's so much better. But here's your sigma squared is your variance. And sometimes we'll shorten that down to var of x, or sometimes you'll see v of x for short. And there's actually more than one formula for it. So if you're looking at the kind of the longer formula, it would be negative infinity to infinity of x minus mu times your PDF f of x dx. That's a little bit harder to calculate sometimes. And so what we do instead is we look at it algebraically, it's equivalent to this, but we look at our variance as the expected value of x squared. And that's sometimes called our second moment. We'll talk about moment generating functions in a different video. The second moment minus the mean squared, so the expected value of x, quantity squared. So notice the squared's on the outside here. Maybe I put even a little extra set of parentheses there. That's your first moment. So you're taking your expected value of x squared minus your expected value of x, quantity squared. So another way to write that would be to take the integral from negative infinity to positive infinity of, we're looking at this x squared part here. So the expectation of x squared would be x squared times f of x dx. So that's this piece in here is the expected value of x squared. And then we would subtract the mean squared. That piece here is your expected value of x quantity squared. We would usually find the mean first and then substitute it in there. You'd have to find the mean first anyways if you did the long formula, but this formula usually ends up being a little bit quicker. And then the standard deviation, sorry, that's your variance. The standard deviation is just going to be the positive square root of your variance. And the advantage of putting things back in the standard deviation is that you get back to the original units, whereas the variance will have units squared. So let's look at an example. I don't know if you've ever put together furniture at home that gets mailed to you and they have pre-drilled holes, and sometimes it's really frustrating if those holes don't match up with one another. And so this particular example is looking at, we're going to let x be continuous random variable that represents the clearance in millimeters for a hole drilled in the wood. And the PDF probability density function for this would be f of x equals 1.25 times 1 minus x to the fourth power for all values of x that are between bigger than 0 but less than or equal to 1, and then the function 0 anywhere else. And we'll ask a couple of different questions off this example. So for here, part A, let's just start with finding a simple probability. So we're going to find, let's see, calculate the probability that the clearance will be larger than 0.8 millimeters. Sometimes it'll be in a sentence. You do have to be careful with qualifying words like less than, greater than, at most, at least, larger, smaller. So just be really careful. I think a picture really helps. So we're going to draw this in a picture. So we're specifically looking at the probability that x is less than 0.8. And this is going to be, with the mathematics behind it, the integral from thinking about this integral. I could go from 0 to 0.8 or 0.8 above. Oops, sorry, I said less than, huh? I just said that. Be very careful. Larger than. So I'm going to go from 0.8, starting at 0.8, up to 1. If I went from 0 to 0.8, I'd have to use the complement rule. And keep in mind that just because sometimes you'll have software packages that will calculate these, what we call cumulative distribution functions, that usually go below a point, but we want larger. Of the function itself, f of x, which is, I can drop the 0 part because I'm not in that range of values. So I'm just going to have this 1.25 times 1 minus x to the fourth dx. So that's going to be the probability of the math that I'm looking at. But I like to draw a picture too, just to make sure that everything seems correct. You could get a graphing calculator, graphing software to do this. But if we were to think about, if I were to plug in, let's just start at 0, x equals 0, x, and f of x. When x is equal to 0, this term would be 0. 1 minus 0 is just 1. 1 times anything else is just 1.25. So this is going to have a point at 1.25. And actually, let me use a different color for my graph, just to have it. And then if I were to plug in, let's say at our boundary point of 1, if I plug in 1, I have 1 minus 1 is 0. 0 times anything else is 0. So I have another point here. And then this is going to be a quartic function. And if you were to graph it, it actually is going to have a downhill kind of curve to it. It's going to go down like this. And then the function itself would be 0 everywhere else. And then we're specifically looking at 0.8, what is that probability? So if I was to think about the shaded area in here, is what I'm trying to find. Sometimes it just helps just to be in the, see if you're in the right ballpark, if you have less than half or more than half of the distribution, if your answer is correct or not. Like the silly mistake I just made with the less than sign, that would indicate, oh, that's going to probably be a number bigger than 0.5 instead of smaller than 0.5. In fact, I didn't even draw this to scale. That 0.8 is probably much closer to the 1, so it's even smaller than a quarter of that, quarter of a circle. So if I look at the math behind this, if I go back to my integral in here, this would be equal to, I'm going to take this constant out front just to make it a little easier to work with. So we have 1.25 from 0.8 to 1 of 1 minus x to the fourth dx. So that would be equal to 1.25. The 1 here becomes x. X to the fourth becomes x to the fifth over 5. And we're evaluating that from 0.8 to 1. So that would be 1.25. And start with the 1. We plug in, substitute 1 in there. I have 1 minus 1/5. And then minus our 0.8 plugged in. We have 0.8 minus 0.8 to the 5th over 5. And that will come out to be equal to 0.019 approximately. So that would be our probability of having a clearance of more than 0.8 millimeter, which is good. You don't want a huge clearance when you have parts that you're putting together. All right, now let's get to the mean and the variance part. That's what we're talking about in this video to begin with. Just want to make sure everybody's on board with the probability density function. We're going to look at calculate the average clearance. So our mu, or expected value of x, in other words, is equal to minus negative infinity to infinity of x f of x dx. And our boundaries are just going from 0 to 1. So we'd have our integral going from 0 to 1 of x times the function. So that would be multiplied times 1.25 times 1 minus x to the 4th dx. Again, pulling that 1.25 out in front of my integral. And then I'm also going to distribute this x term through the parentheses. So I would get x minus x to the 5th dx, just to make it a little bit easier to do that integral. That's equal to 1.25 times x squared over 2 minus x to the 6 over 6, evaluated from 0 to 1, which would be 1.25. And if I substitute the 1 in here, I would get 1/2 minus 1/6, and then 0 for the 0 squared and 0 to the 6th power up on top. That would come out to be equal to, you could keep it in a fraction form, it would be 5/12, to be exact, more approximate value, 0.4167 millimeters would be the average clearance. All right, and then part C, calculate the variance of our random variable clearance value. So we would have sigma squared equals, again, that expected value of x squared minus expected value of x quantity squared. So we did just calculate this piece in here. So we're going to concentrate right now on calculating first the second moment, we call expected value of x squared. If we were looking at just that piece, we would have the integral from negative infinity to infinity of x squared times f of x dx, or in our case, in this example, from 0 to 1 of x squared times our 1.25 times 1 minus x to the 4th dx. And then that is equal to, I'm going to bring our 1.25 constant out in front of the integral. And then I'm going to distribute the x squared through both terms. So x squared times 1 is x squared, and x squared times x to the 4th is x to the 6th. And then integrate, we get 1.25 x cubed over 3 minus x to the 7th over 7, evaluated from 0 to 1. And that would be 1.25 multiplied by 1/3 minus 1/7. Right, and that's going to be, let's see, do that one in my head. I'll clean that out real quick. 5/21st, which approximates out to 0.238095. That's not the variance though, so I did that in a different color because that's just part of our answer. So the variance is going to be that 521 value minus our mean squared. So recall that the mean was 5/12 squared. I use the fractions because ideally you never round between steps, but if you are going to use the decimals, go out at least 6 decimal places between steps so that your answer out to 4 isn't too far off. And that comes out to equal approximately 0.0644 millimeters, but our units are squared in this case. So that would be our answer to the variance. And then let's do part D. Calculate the standard deviation. That's just simply the square root, positive square root of the variance. So if we were to take hold on, sorry. I am just calculating real quick. Right, that comes out to be 0.615. And I took the whole number rather than rounding, but I just wrote out to 4.2539 millimeters. All right, there is your video on finding the mean, variance, and standard deviation for our continuous probability distribution.